Welcome to the final part of our Boundary Layers series on Pump Design Lab. We now understand why boundary layers form, how they become laminar or turbulent, and how they can separate. The final question is practical. What can a designer do to control this behavior and reduce the losses it creates? What is boundary layer control? Boundary layer control means deliberately managing the near wall flow so that it remains efficient and attached. The aims are to reduce friction losses, delay separation, improve pressure recovery, and reduce unsteadiness. Some methods are passive and come from geometry. Others are active and use added energy, suction, or injective flow. Although many control techniques exist, they all follow two simple strategies. Two ways to prevent separation. Nearly every boundary layer control method can be understood using two simple rules. First, give the weak near-wall fluid more momentum. Second, reduce the adverse pressure gradient that the near-wall fluid must overcome. Some methods do one of these. Some do both. This is the central logic behind the entire control toolkit. The first and most powerful strategy is to prevent an excessive pressure rise from appearing in the first place. Control Method 1. Shape the pressure gradient. The cleanest and most powerful method starts during design. Do not create an unnecessarily severe pressure rise. Use smooth curvature, gradual area changes, and well-distributed blade loading. If the flow is turned and decelerated over a longer distance, the boundary layer has a much better chance of remaining attached. Diffuser design gives us a very clear example of how geometry controls the pressure gradient. Diffuser angle control. Diffuser design is a classic example. A diffuser must increase pressure, but it should not do so too suddenly. A longer diffuser with a gentler divergence angle normally gives the boundary layer more chance to survive. If the included angle is too large, separation becomes likely. Practical simple diffusers often use conservative included angles, commonly in the approximate range of 8 to 12 degrees, depending on application and inlet conditions. The same philosophy applies inside the impeller, where blade curvature and loading determine the pressure recovery along the passage. Blade curvature and loading control. The same discipline applies to impeller blades. Avoid sudden changes in blade angle and avoid concentrating too much turning near one small part of blade. Spread the velocity and pressure change smoothly along the camber line. Smooth loading reduces the severity of suction side adverse pressure gradients and makes separation less likely. When geometry alone cannot prevent separation, engineers may sometimes use a second strategy, deliberately energizing the boundary layer. Control Method 2. Trigger turbulence deliberately. Sometimes a designer deliberately promotes turbulence to avoid a larger separation loss. This is the golf ball idea. A turbulent boundary layer creates more skin friction, but it also has more momentum near the wall. If that extra momentum delays separation significantly, the total loss can be lower than with a smoother but weaker laminar boundary layer. One passive way to do this is with vortex generators. Vortex generators. Vortex generators are small tabs or vanes placed on a surface. They create controlled streamwise vortices. These vortices pull high-momentum outer fluid down toward the wall and lift slow near-wall fluid outward. In this way, they re-energize the boundary layer and can delay separation. They are common in aerospace and may be used in selected turbomachinery applications. A more direct but more complex technique is boundary layer suction. Boundary layer suction. Boundary layer suction removes the slowest fluid next to the wall through slots or porous surfaces. By extracting this low-momentum fluid, the remaining boundary layer becomes thinner and relatively stronger. It can resist a more severe adverse pressure gradient. Suction can be highly effective, but it requires hardware, ducting, and power, so it is not common in ordinary centrifugal pumps. The opposite approach is to add momentum directly through boundary layer blowing. Boundary layer blowing. Boundary layer blowing does the opposite. Instead of removing slow fluid, it injects a thin jet of high-momentum fluid along the surface. This directly boosts the near-wall flow and can delay or even reattach separation. It is like giving our tired cyclist a push uphill. Again, the method needs energy and added complexity, so it is usually limited to specialized designs. There are also practical geometric and surface-based tools that influence near-wall flow. Splitter vanes, surface finish, and riblets. Splitter vanes are a practical geometric method for wide diffuser passages. By dividing one wide passage into narrower passages, they reduce the effective diffusion demand and help control separation. Surface finish also matters. Smoother surfaces generally reduce friction. In specialized applications, tiny streamwise grooves called riblets can modify near-wall turbulent structures and slightly reduce turbulent skin friction. At this stage, the important realization is that boundary layers are not isolated effects. They are present across the complete hydraulic passage of every pump. Boundary layers are everywhere in pump design. At this point, we can see that boundary layer science is not a separate topic sitting outside pump design. It is present in every hydraulic passage. Every wall creates a slow layer. Every bend, expansion, and pressure recovery process tests that slow layer. The quality of pump hydraulic design depends greatly on how well these layers are managed. Let's now connect all the physics through one simple cause and effect chain. The chain of events. The chain is straightforward. Wall friction creates slow near-wall fluid. That fluid contains less momentum than the outer flow. If the passage creates a strong adverse pressure gradient, the slow fluid loses forward motion. Separation follows. Then recirculation, pressure loss, non-uniform velocity, noise, vibration, and lower efficiency can appear. This chain explains why real pump design is more demanding than simply calculating theoretical Euler head. The core pump design challenge. A pump is not simply a device that adds energy to liquid. It must add energy while guiding the liquid through rotating, curved passages without creating excessive loss. Euler's equation gives a theoretical energy transfer. But the difference between theoretical and actual pump performance is shaped by friction, boundary layers, secondary flow, mixing, leakage, and separation. One of the clearest examples of design stage boundary layer control is smooth blade loading. Why smooth blade loading matters. Smooth blade loading is not merely an aesthetic preference in CAD. It controls how pressure changes along the blade. When the pressure recovery is spread smoothly, the boundary layer can remain attached. When the blade asks the flow to turn or decelerate too abruptly, the low-momentum near-wall fluid is more likely to separate. Good blade design is boundary layer control built into the geometry. The same discipline is essential in the diffuser, where the desired pressure recovery can be lost if expansion is too aggressive. Why conservative diffuser design matters. A diffuser is supposed to recover pressure, but pressure recovery only works if the flow remains attached. An overly short or steep diffuser may look compact and may promise strong theoretical recovery, but separated flow can destroy that benefit. In many cases, a gentler diffuser with lower ideal recovery can deliver better real recovery because the boundary layer remains attached. Even a good hydraulic design can experience stronger losses when the pump moves away from its intended operating point. Why off-design operation matters. At the best efficiency point, flow enters and leaves the pump passages close to the intended angles. At part load or overload, incidence changes. These changes can increase blade loading, strengthen adverse pressure gradients, and enlarge separated regions. This is one reason efficiency, vibration, and hydraulic stability often deteriorate when a pump operates far away from its best efficiency point. Those off-design losses do not affect efficiency alone. They can also affect vibration and long-term reliability. The link to efficiency, vibration, and reliability. Attached flow supports good pressure recovery and high efficiency. Separated flow wastes energy and creates unsteady recirculation. That unsteadiness can cause pressure pulsations, noise, and vibration. Over time, vibration can add stress to bearings, seals, shafts, and structural components. Boundary layer management therefore matters not only for efficiency, but also for pump reliability. We can now reduce the whole topic to one clear sentence. The one-sentence explanation. Here is the one sentence to remember. A boundary layer is a thin region near a solid wall where friction slows the fluid down. It becomes dangerous when this low-momentum fluid cannot overcome a rising pressure and separates from the surface. That separation is one of the most important causes of loss and instability in real hydraulic machinery. And we can reduce the entire control philosophy to two equally clear rules. The two rules of boundary layer control. And here are the two design rules to remember. First, give the near wall fluid more momentum using methods such as controlled turbulence, vortex generators, suction, or blowing. Second, reduce the pressure rise it must fight using smooth blade loading, gradual diffusion, controlled curvature, and splitter vanes. In most pump designs, the second rule is the most practical and powerful. Let's finish by bringing the lesson back to practical pump design. Final takeaway. Boundary layers may be thin, but they control a major part of real pump performance. They explain why ideal flow calculations are not enough, why diffusers need careful angles, why blade loading must be smooth, why off-design operation creates losses, and why separation can lead to vibration and cavitation risk. Good hydraulic design is, in many ways, the art of keeping flow attached for as long as possible. If this episode helped you see pump flow more clearly, subscribe to Pump Design Lab. In the next topic, we can connect boundary layers directly to hydraulic losses, slip, and the difference between theoretical and actual pump head. You have now completed the boundary layers and boundary layer control series. Remember the main message. Boundary layers are thin regions near walls where friction slows the fluid. If the slow near-wall fluid faces too strong a pressure rise, it separates. Good pump design protects the flow by keeping pressure recovery gradual and by maintaining enough momentum close to the wall. If you found this series useful, subscribe to Pump Design Lab. In the next episode, we can connect boundary layer losses to slip, hydraulic efficiency, and the difference between theoretical and actual pump head.